In this lecture, we shall find the shear force and bending moment values for a simply supported beam with a concentrated moment acting at the center of the beam. As usual, a simply supported beam is drawn with the left end pinned and the right end connected to a roller support. We label the ends as A and B respectively and the center of the beam as C, where a clockwise concentrated moment of value m kilonewton meter is shown acting. The projections from these key points are dropped and the lengths are dimensioned. To find the unknown reactions at the supports, we assume RA and RB to act vertically upwards tentatively. Now, considering the entire body in static equilibrium, summation of forces in vertical y direction, that is RA plus RB equals 0. Let us label it as 1 for later reference. Also, summation of moments say about end B equals 0, that is L times RA plus M equals 0, since both produce sagging moments about B. Hence, Ra equals minus m over L kilonewtons. Negative sign indicates that the actual direction of Ra points downwards instead of the assumed upward direction. We show the same on the end A of the beam with a thick arrow. From equation 1, Rb equals plus m over L kilonewtons, positive sign indicating that the assumed upward direction of Rb is retained, and hence we denote Rb by a thick arrow. We now mark the left end A as the reference from where the distance x of the imaginary section is measured and apply the method of sections to find the shear force and bending moment values at various sections along the beam length. Then we draw the zero datum lines for shear force diagram and bending moment diagram respectively. For region AC, for which x is greater than or equal to 0 and less than or equal to 1/2 L meters, the shear force at x equals minus m over L kilonewtons, which is a constant. For region CB, for which x is greater than or equal to 1/2 L and less than or equal to L, the shear force at x again equals minus m over L kilonewtons, a constant value. The values are plotted in the shear force diagram. Now the bending moment at x for region AC equals minus m over L kilonewtons times x meters, which is linear. For region CB, bending moment at x equals minus m over L times x plus m kilonewton meter, which is also linear. We apply the limit values for the two regions to find the bending moment values and plot it in the bending moment diagram accordingly. The maximum bending moment is seen to vary from minus half m kilonewton meter at the center considering the first half of the length to plus half m kilonewton meter at the center considering the latter half. We can logically investigate whether the actual directions of the reactions at A and B obtained analytically are really correct or not. If it is imagined that the supports are absent in the presence of the central clockwise moment, the beam has a tendency to rotate clockwise about the center as a pivot. What the presence of the supports at A and B actually does is to arrest this rotational movement by invoking the reactive forces at the supports. The reactive forces as calculated analytically produce a counterclockwise couple of value m over L kilonewtons times L meters, which is m kilonewton meter, the same value as that of the applied moment at C, and hence the beam is statically balanced. This proves that the directions obtained analytically for the reaction forces are indeed correct. Let's now investigate the case where the simply supported beam, as discussed earlier, is acted upon by a counterclockwise moment at the center instead of the clockwise moment. From analytical calculations, Ra equals m over L kilonewtons acting upwards and Rb equals m over L kilonewtons acting downwards. We denote them on the beam for clarity. Here we find that Ra acting upwards is logically and practically possible in direction, while Rb acting downwards is illogical and impractical since the roller support offers resistance to motion only in downward direction of the beam end and resistance is not offered in upward direction of the beam end. Hence, for the given supports and acting moment at the center, the perceived counterclockwise rotation of the beam about the center, if the supports were absent, would actually tend to topple or rotate the beam counterclockwise about the end A acting as pivot, since the downward movement of the left end is arrested, while the right end of the beam tends to move upwards as long as acting moment M is present, making the beam unstable and static equilibrium ceases to exist. To make the system practical and in static equilibrium, we may modify the given roller support so that the resistance to motion is also offered to the upward movement of the right end of the beam as shown here. Note that the modified roller support continues to provide reaction force in only one direction, that is vertical, but now both in upward and downward direction, and that the horizontal reaction force and reaction moment are not offered, hence the number of unknowns for the support still reads as 1. In the next lecture, we shall analyze a simply supported beam for shear force and bending moment with a symmetrical triangular load, also known as uniformly varying load, acting over the entire length.